so it's 12 o'clock. We'll go ahead and get started. So the test was on Friday. I did start marking, so it's half marked. So I mark a couple of the questions, and one of our TAs, Audrey, who's a TA in the Thursday lab, she marks the other two questions. She's getting started today, so hopefully it won't take that long. Does anybody have any comments, feedback about the test? How do you think it went?
Was the first question actually worded 6 points or 10?
6.
Okay, cool.
Yeah, I changed it last minute, so I changed the points, and I made it kind of a fair bit easier. The original version of that test, I had you solving that question.
Sick.
And I decided in the end, I didn't care so much about solving the algebra of the equations as I cared about seeing how you set it up, so it went from 10 down to 6. Yeah, so I forgot to change it in there. Okay, so that's done. We're kind of scarily close to the final exam, so that's coming before you know it. The final exam will be more or less like the term test, only a bit longer. It will cover the whole semester, and you will be allowed to bring in a sheet of notes if you wish. So kind of feedback on the sheet of notes. Do people find it valuable?
Yeah.
Not valuable? Yeah, okay. That's good.
Especially if you have like a bunch of terms, like with in the first term test, the wavelengths,
Yeah.
trying to remember those.
Oh, yeah, okay. All right, okay, yeah.
It'd be nice to have the formula sheet earlier so we can tailor our notes to that.
I will do my best. In the meantime, because I post it kind of as soon as I'm done, right? And sometimes I don't finish right away. In the meantime, I will post a couple of old final exams. The formula sheet won't be very different, but absolutely I can get that released pretty soon. Yeah. Okie dokie. So last day we did a lot about capacitors. We know they're circuit devices that store electrical potential energy. We talked about RC circuits. They have a current that turn off and on where the size of the resistor and the potential supply controls the current. We know it takes an amount of time both to charge and discharge. Today we're going to go through some examples. We might get to magnetism today, we might not. It's kind of okay either way. So before we start, does anybody have any questions? Okay, so let's jump in with some examples. So when I posted new slides the other day, this is the second of those 2 new slides. So we'll go through that one now. This is similar to the example we did in class last time. We talked about a charging circuit, and I had in the same capacitor and the same resistor. But now we're going to apply those ideas to the discharging circuit and see what we get when we do that. So to get started, for our circuit shown, we know that our capacitance here is 1.77 times 10 to the minus 12 farads. Our resistance is 100 ohms. We're going to close the switch at t equals 0. So at t equals 0, this is going to come down. We're going to complete the circuit. We know that current's going to be allowed to flow. The capacitor is going to start to discharge. The capacitor is initially charged to a potential of 1.5 volts. So 1.50 volts to start and 1.77 times 10 to the minus 12 farads for the capacitance. Right off the bat, we could find that charge if we wanted to because we know Q is capacitance times potential. So we could find that if we want. Okay, part A, when the switch closes, so right at t equals 0, what's the potential across the resistor and across the capacitor? It's really easy to answer the capacitor question. So it was given in the setup. So, I think I can get most of this up on the screen at the same time. Question mark. So part A, the potential across the capacitor equals 1.50 volts, and we know that because it's given. For across the resistor, well, it's a closed loop. It's got 2 circuit elements. The net potential around any closed loop has got to be 0. So however much potential is supplied by the capacitor also has to be dissipated in the resistor. So delta V of the resistor equals 1.50 volts. So that comes from our potential law. So we know what the potential there is. Part B. When the switch closes, what's the initial current through the circuit and what's the initial charge on the capacitor? So we know as soon as it closes, those charges here are free to move. They're repelled by each other, so they're going to start flowing around the circuit. As they start flowing around the circuit, that means we get a current flow, so we're asked for that current and that charge. So let's do the current first. We know that the potential difference across the resistor is 1.50 volts. And according to Ohm's law, V equals I times R. So that means our current is our potential, 1.50 volts, divided by our resistance of 100 ohms, to get a current of 0.0150 amps, or 15 milliamps if you like milliamps better. Okay, so that's the initial current in the circuit. For our initial charge, so the charge on the capacitor at T equals 0. In our previous notation, we called that Q with a little 0 by it. Some places might call that Q maximum, that's okay too. That's going to be the potential across the capacitor at T equals 0 times the capacitance. So 1.50 volts times 1.77 times 10 to the minus 12 farads. Put that into the calculator and we get 2.655 times 10 to the minus 12 coulombs. So that's the initial charge on the capacitor. We know over time that this is a discharging circuit, so those are our maximum values. Those are going to decrease over time. So we might call that I0 as well. Okay, part C, what happens to the current and charge on the capacitor over time? What happens to the potential across the resistor and the capacitor over time? So everything is decreasing because this is a discharging circuit. So C, everything decreasing. We can find expressions for how that's decreasing. For our current, we know that our current as a function of time is the maximum current times e to the minus t over tau. Tau is our time constant. Remember that that's R times C. So our time constant is 1.77 times 10 to the minus 10 seconds. For our charge, that's also decreasing over time. So Q as a function of time is QO, e to the minus t over tau. So there's our current and our charge. We can also do our potentials. Delta V across the resistor as a function of time is the current as the function of time times the resistance. So I0 times R e to the minus t over tau. If we look at this, I0 times R, that was our initial potential across the resistor. And then for the potential across the capacitor, two ways you could answer this. You know it has to be the same as the potential across the resistor because they're in a closed loop together. Or you could also do it by knowing that your V of the capacitor is the charge as a function of time divided by the capacitance. So QO over C e to the minus t over tau. We can recognize that QO over C gives us that initial potential across the capacitor, 1.50 volts, e to the minus t over tau. Okay. So two ways to get to the same answer there. Part D, we did part D while we were thinking about it. Find the time constant for this circuit. That was our tau equals RC. So our time constant, 1.77 times 10 to the minus 10 seconds. Part E, how long does it take to become approximately fully discharged? Here's where we're talking about, we know discharge is after 5 time constants. So that time is equal to 5 tau. 8.85 times 10 to the minus 10 seconds. That is very fast. Okay, any questions? So that kind of takes us through all the different things you might need to know about a discharging circuit. Okay, let's go through another example. if you downloaded the notes, I think I made a couple of changes to the diagram. So if you printed them off or if you downloaded them, initially the switch was in contact with A. I just drew it so that it wasn't in contact yet. And I don't know if this resistor was here before or not, but it is there now. So 50 ohm resistor down here next to the battery. So I made those couple of changes to make this problem more in line with what we've been doing so far. So the system shown initially has a switch not making contact. At t equals 0, we switch it to position A after 5 time constants, and it does mean the time constant for this part of the circuit. We flip it to position B. And then, because it's a class example instead of a test example, I asked a very vague question, describe the charging current over time. So let's use this as a springboard to talk about what happens in a kind of circuit that first starts with a discharged capacitor, flips over to a battery supply. So we know that when it's flipped here, it's going to start to charge. Then we're going to flip it over here to where it's connected to a resistor. It's going to start to discharge. So this is the kind of circuit where first it charges up, then it discharges. This is one of those timekeeping circuits, right? It turns off and on over and over. So let's start to think about what happens. So first of all, in the beginning, before we flip any switches, t less than 0, the capacitor is uncharged. And there is no current flow. So before we connect anything, nothing's happening. So that's not a very interesting result, but it's good to know where we start. At t equals 0, we're going to flip the switch to part A. So let's draw the circuit diagram. Got my 9-volt battery. I'm going to give that a symbol of epsilon for EMF. It's connected to my 50 ohm resistor down here. I'm going to call this R1. It's connected to my capacitor here. I'm going to call this C. Come up here, and the switch is in position at A. Then over here on this side, got my second resistor, R2, my 25 ohm resistor. Okay, sometimes it's easier to have symbols instead of numbers. So right at this moment, when we flip the switch, let's ask what starts to happen. So what's going on is that on this branch of the circuit, the capacitor starts to charge. That's what's going to happen over on this side. Over on this side, this piece of wire is not connected to anything. We can't get a current flow in this branch because that's an open circuit. So right at the very beginning, when t is equal to 0, at the very beginning, the capacitor is starting to charge, but no charge has collected yet, so the initial charge on the capacitor is going to be 0. It hasn't had time to build up. So let's put that in there. So Q at time t equals 0 equals 0 because it hasn't had time to charge yet. My potential difference across the capacitor, delta V of the capacitor, equals Q over C equals 0. So there's no potential difference across the capacitor because there's no charge on it. So the potential difference across the resistor, delta V across R1, has got to be all of the potential difference of the battery. We know the potential difference across the resistor, and we know the resistance, we can find the current. So the current at t equals 0 equal to the potential difference divided by the resistance, 9 volts over 50 ohms, 0.18 amps. That's going to be the max value. So we could call that I0. Everybody okay with what's happening at the beginning?
So even though there's nothing in the capacitor at t equals 0,
Yep.
there is still current that or well, yeah, I suppose it would be the stuff getting pulled from the other side of the capacitor to the battery.
Yeah, it's just starting to go, right? So some charge is moving, but it hasn't had time to collect on the plates
The
yet.
entire loop moves at
Yeah.
the same time.
Yeah, exactly, so it's all going at once. Okay, so that's at t equals 0. So the next interesting bit is what happens between t equals 0 and 5 time constants. So that's when the capacitor is charging. This potential is going to increase, this potential is going to decrease, this charge is going to get bigger, this current is going to get smaller. So that's what's going to happen in the next little bit of time. So between the time of 0 and 5 tau 1, so the first time constant, right off the bat, let's find our tau 1 equals R1 times C, 50 ohms, times 4 microfarads. That first time constant is 2 times 10 to the minus 4 seconds. Okay, so we're talking about what happens in the first 5 time constants. So what happens is capacitor begins to charge up. So the charge on the capacitor is going to be QO. That's going to be our maximum charge, times 1 minus e to the minus t over tau 1. Capacitor charging. QO is the maximum amount of charge. We'll get the maximum charge when the full potential is across the capacitor. So QO is Q maximum equals the full potential times the capacitance, 36 microcoulombs. For our current flow, the current flow is going to be decreasing I0 e to the minus t over tau 1. Current decreasing. And then I0 was the value we already found, 0.18 amps. So that's what's happening with the charge and the current in the first part. So that's giving us the current through the branch, the charge on the capacitor. And we already established at the beginning there's no current through R2, so we don't have to write down any equations there. We've already said what that is. Any questions? So that's what's happening with charge and current over time. If you wanted to write down your expressions for potential, you could do that as well. So the potential across the capacitor is Q divided by C. Potential across the resistor is I times R. So you could write those equations as well. Potential here is decreasing, potential here is increasing, potential here is decreasing. So the next interesting thing, the next thing we'll look at is what's going on at t equals 5 times tau 1. So t equals 5 times tau 1. So that time, right before we flip the switch, so all of the potential is across the capacitor. So on the capacitor, delta V equals 9 volts. Q is equal to our maximum charge, 36 microcoulombs. And across this resistor, delta V equals 0, I equals 0. So right before we flip the switch, and then after we flip the switch, now our circuit looks like this. R1, C, battery, R2. Okay, so we're flipping at tau 1. It's kind of switching right there at that point. So just before we switch it, our capacitor has this full potential and this full charge. So right after the flip, the capacitor still has the same potential, delta V equals 9 volts, and the charge is still 36 microcoulombs. And if we look at what's happening in this circuit now, there's nothing happening over on this side because this is not connected anymore. And there was no current anyway before we flipped it. No current. What's happening now on this side is that charge is allowed to flow off these plates. So the charge is going to start to flow around. We will get a current, and this capacitor is going to start to discharge. So capacitor discharges. So when it was flipped in this position, that's when we got it all charged up. We flip it to this position, it starts to discharge. So let's think about what it means. That now we're in a closed loop here with this capacitor and this resistor. The potential across the capacitor is 9 volts. They're in a closed loop, so the potential across the resistor also has to be 9 volts. Delta V equals 9 volts equals X. We know the potential across the resistor, we can find the current through the circuit. So charge is flowing, it means there's a current, so we can find that current. I is equal to delta V divided by the resistance, R2, 9 volts, divided by 25 ohms, 0.36 amps. And that's going to be our maximum current, I0. So that's the biggest the current is going to be because the capacitor is starting to discharge. You're still with me? So now, after 5 time constants of this circuit, that's when everything will be discharged. So let's talk about what happens over those next 5 time constants. So from t equals 5 times tau 1 to 5 tau 1 plus 5 tau 2. Okay? So what happens over the next 5 time constants? Our capacitor is discharging. So that means Q on the capacitor is equal to Q0 times e to the minus t over tau 2. Tau 2 is the time constant of the second circuit, R2 times C. R2 was 25 ohms. Our capacitor was 4 microfarads. So our time constant in the second circuit, the discharging circuit, is 1 times 10 to the minus 4 seconds. And our Q0, that was the maximum charge, the charge at the beginning, that was our 36 microcoulombs. And then for our current, that's decreasing over time. That's I0 e to the minus t over tau 2. I0 is that maximum current, 0.36 amps. So it's discharging, and that's how it goes. Again, you can write the potentials here if you want to. Remember, delta V is Q over C, or I times R. You can get your potentials there. And then after this time, everything's discharged, no current, no potential anywhere. So after 5 tau 1 plus 5 tau 2, so here's where it charged up. Here's where it discharged. Everything is 0. So the charge on the capacitor plates, potential across the plates, current through the resistor, and potential across the resistor. It all goes to 0 because it's all been discharged. Any questions? Yeah?
So like, as you're doing examples and you're going through and you're thinking like, alright, so now the potential's gonna go up, or like this current's gonna go down, like, do you picture anything in your head, like, that distinctifies like current from potential, for example, or like charge, like, how do you think about it?
How do I think about it? I picture the little charges moving around the circuit,
Right on.
right? So when we put our initial pictures in, we often have pluses and minuses on the plates. I imagine the pluses moving, right? So the ones that are on the plate are the charge on the plates, the ones that are moving are the currents. And then the potential is across the whole device, so between the positive at one end and the negative at the other end.
Okay.
Yeah, kind of how I see it. There are probably lots of different ways to
Oh
visualize
yeah,
it.
I was just curious how you
Yeah.
think about it.
Okay, so let's move on. I had this one in the notes. As I was going through it yesterday, as I was getting ready for today, I decided that conceptually, maybe this one's just a bit too much. So let's mark this one as a Jedi problem, that if you want to have a look at it at home, just to kind of stretch your understanding, you're absolutely welcome to. Don't look for this one on the test. Okay, so we'll put a Jedi on this. I'll post the solution if anybody's interested. But that's kind of above and beyond what I'm expecting you to be able to come up with in a test environment. However, I didn't want us to have kind of a blank set of examples. So at the last minute this morning, I did come up with a new example. Sorry about not posting it in time, but it was super last minute. And I thought this is nice because this brings us back around to an application. I said that we use capacitors and circuits where we require kind of a discharge of charge. And an example would be like the flashlight on your cell phone, the flash on your cell phone, or on a digital camera. So when you want to take a picture with a flash, typically you turn on the camera, you turn on the flash, you take your picture. You can't get another flash right away, right? You can only get it once, then you have to wait a little bit, then you can get it again. That's this circuit right here, right? So this is the circuit on the circuit board in your phone, letting the phone flash go on. So we put a switch in place, and I'm just trying to talk for a bit in case people want to write down some of these numbers. I'll post it after class too. So what happens is initially, before you take your picture, the circuitry closes this switch. We've got a battery, a resistor, and a capacitor. With that switch closed, the capacitor starts to charge. Okay, so we get the capacitor charged up. It stores a whack of energy. When you're ready to take your picture, we come to this circuit. You press the shutter, that closes this switch, and this capacitor supplies the energy to the flash. Okay, that's what happens. It uses up the energy, then we have to open that switch, close this one again, let that charge up, and then we can take another flash picture after that. So that's kind of how flash photography works.
Sorry, real quick, what's the symbol for a light bulb? Like in a
Oh, that's just a resistor,
Oh, okay.
so like that. So doing a circuit diagram, that's what you draw. Your book really likes drawing light bulbs. So this question is asking, how long does it take to charge the capacitor to 5 volts? So this is not a really tough question, but it is a nice illustration of the kind of circuitry we use this for. So let's draw a picture. So how long does it take to charge? So we're looking at the charging side of this problem. So to get it to charge, we've got our potential supply here. That's our 9 volts. We're connected to this resistor. I'm going to call this R1. That controls the amount of current going through the circuit. That comes over here. We've got a branch to the capacitor. That's the device that's storing the energy. And if we want to get it to charge, we close our switch S1. And then over here on this branch, you can draw it or not draw it. Doesn't really matter that much. The switch is open, so nothing's happening on that side. So once we do this, we are now charging the capacitor. The total charging process happens between 0 and 5 times the time constant. And that's how long it takes to get completely charged up. We know that when it's completely charged, all of the potential will be across the capacitor, all of the 9 volts. This problem is asking what happens kind of partway through. How long does it take to get to 5 volts? It's not the full charge. So we expect our answer is going to be somewhere between 0 and 5 times the time constant. So that's the answer we're looking for here. So if we want to write down our equation for potential across the capacitor, we know that that's the charge across the capacitor divided by the capacitance. It's a charging circuit, so that's going to be the maximum charge times 1 minus e to the minus t over tau. That's divided by c. QO, our maximum charge, divided by C, equals our maximum potential, which is the potential of the battery, which is 9 volts. So the potential across the capacitor as a function of time is the maximum potential times 1 minus e to the minus t over tau. Okay, so we used our expression for charge to get ourselves an expression for the potential. The reason we want an expression for potential is we're asked to find the time that it's at a certain potential. Okay, so we want to talk about potentials. So as the charge increases, the potential increases, and eventually we'll get to some maximum value of 9 volts. At this point, let's put in the numbers that we know. Or, why don't we stay in symbols for a minute first, actually. Divide both sides by the EMF of the battery. So delta V of the capacitor divided by EMF is 1 minus e to the minus t over tau. I'm trying to get my t, so I'm going to bring my e to the minus t over tau to the left side, and my potential stuff to the other side, 1 minus delta V across the capacitor divided by epsilon. It might be a while since you've done this sort of manipulation. If we want to get our t, it's buried in the exponent of something to a natural number, so you have to take the natural log of both sides. That's how we get rid of the e. So the natural log of this side is the natural log of this side. When we do the natural log of e to the something, we end up with just the argument, minus t over tau, equals the natural log of 1 minus delta V divided by the EMF. Kind of getting somewhere here now. Multiply both sides by minus the time constant. And then our very last bit, we can put in that the time constant is our resistance, R1, times our capacitance, C, times the natural log of all this stuff. If you were more of a numbers person than a symbols person, you probably would have put your numbers here on this line. If that's you, that's fine. I kind of like symbols better, so I kind of stuck with the symbol notation to the end. Either way, you're going to get the right answer. So let's put our numbers in. We've got minus. Our resistance is 50 kiloohms, so 50 times 10 to the 3 ohms, times our capacitance of 140 times 10 to the minus 6 farads, times the natural log of 1 minus the potential across the capacitor. It said we're trying to get to 5 volts, divided by the EMF, which is 9 volts, gives us an answer of 3.77 seconds. So it actually takes a fair amount of time, right, a countable amount of time, to start charging the capacitor enough to get your flash to work. If we wanted to check our answer, why don't we figure out what 5 time constants are? So total time equals 5 time constants. 5 times R1 times C, that's actually 35 seconds. Okay. So in some devices, it might take as long as a half a minute before you can use your flash again, sort of depending on what you've got in your circuit board. Okay, any questions? And I would say kind of if you're thinking about test level and everybody's sort of thinking about the final exam, kind of this would be the speed of the final exam, or those summary questions, those new slides I posted were kind of step by step what's happening. So those would be decent examples to study for this. So one last question. This one should be really quick to go through. Let's start with 2 charged up capacitors. Which one is going to discharge more quickly after the switch is closed? So I'll give you a minute to see if you can figure it out, and then we'll compare answers.
For the final,
Yeah.
how much do you think you're going to weigh each chapter? Like, are you going to weigh it evenly between different chapters, or are you going to focus a little more on individual chapters for the final?
I try to shoot for an even distribution over the whole course. Sometimes you might get an extra question from the end part, you haven't tested on it yet, but reasonably even. Do we have answers yet for A or B? Which one is gonna discharge faster?
I think it's A.
One vote for A. Any agreement? Any disagreement? Everybody else just kind of spacing out? Kind of okay too. All right, so let's see if we can figure out the discharge time. So our discharge time is 5 time constants. So that's 5 times the resistance times the capacitance. 5 times 2 ohms times 6 microfarads. So 5 times 2 times 6 gives us 60 microseconds. That's pretty fast. For B, 5 time constants here. It's 5 times R times C. 5 times 3 ohms times 5 microfarads. 5 times 3 times 5 gives us 75 microseconds. This one's faster, so this one wins. So the 2 people who committed to an answer were absolutely correct. Questions? So the last section of the course, I think it covers chapters 27, 28, and 29. I went through all 3 chapters and I kind of picked and chose what I thought was the most relevant parts to Physics 1051. So we're not going to do all parts of all chapters. And I posted all of the notes to the end of the semester, and I think I called it chapter 27 plus. Okay, so everything is up now for all the lecture notes for the rest of the semester. Unless I start tinkering and putting new notes, who knows. So let's get started on that. My favorite example of magnetic field application, we will get to talking about that. The first section of the book is pretty good. I know not everybody likes Wikipedia, but you know, physics parts of Wikipedia is pretty good because physicists don't tend to let wrong stuff stay up for very long. So those are a couple of places where you can get some nice background reading. A couple of things that are neat, but you don't have to read it. I won't test you on it. So magnetoreception, we'll talk a little bit about that in class. And this last bit here, nature of things when north goes south, if you can find this, it's really cool. It's about the Earth's magnetic poles flipping and the fact that we're overdue by, you know, a few thousand of years now. So that's cool. So magnetism is really, really old. I guess as long as we've had people on the planet, people have understood magnetism and looked at it. So this has been around forever. Kind of about 3,500 years ago, we have evidence of Chinese people using a compass. So we kind of have some long-standing evidence there. Just floating a needle in water. So that was kind of the first compass. You put a little magnetic needle, float it in water, and it will line up with the Earth's poles. Around 800 BC, it's attributed to the Greeks that they discovered that magnetite would attract pieces of iron, so they were seeing magnetic forces to think about. When we get to the 1200s, Marico, a French physicist, he actually coined the terms North and South Pole, and he started to talk about the Earth as a giant magnet, so that was then. We got to 1700, talking about the forces between magnetic poles and investigating those. Then the neat stuff happened in the early 1800s. So we saw that electric currents in wire make magnetic fields. We saw that changing magnetic field made changing electric fields. And all this stuff was interconnected and kind of that birthed electromagnetism. And we see that electric fields and magnetic fields, not only are they linked, but they're kind of the same thing. And that'll be the very last thing we do in this course is talk about why an electric field is the same thing as a magnetic field. And that's just kind of a point of view. Okay, so first place we'll start is a review and a comparison between electric fields and magnetic fields. So our electric fields had symbol of E. It had units of newtons per coulomb or volts per meter. We know that electric fields are around charges. We represent them with lines going out of a positive into a negative. We know that like charges will repel, unlike charges will attract. We know that that's action at a distance, so it's not one of the forces that have to touch, it's a field force. And this is interesting, and here's where fields, electric and magnetics are different. We certainly know we can have a single charge. A proton can sit by itself, or an electron can sit by itself. They don't have to come in pairs. Magnetic fields have units of Tesla after Nikolai Tesla. He was sort of mid-1800s to mid-1900s. Serbian American. He was really cool. He wanted free electricity for the entire world. He kind of conceptualized Wi-Fi, right? So Tesla is the guy who should have credit for Wi-Fi, even though he doesn't get a lot of love. There was an episode of Doctor Who, the 12th Doctor, who interacted with Nikolai Tesla. That was cool too. Not required reading for the class. So there's two ways to get a magnetic field. You can just have a magnet, like you stick on your fridge, so that makes a field, or a moving charge or current, so we're going to spend some time talking about that. All magnets have two poles, and this is really neat. Well, we're going to talk about these two things first. The Earth itself is a giant magnet. If you have a magnet, the north pole of this magnet will point towards the Earth's geographic north, or close to it, not spot on, just kind of close. People think of it, the north of a magnet is always painted red because Santa is at the North Pole. And the south pole of a magnet will point close to the south pole of the Earth. That means that the south pole of the Earth is a magnetic north and the north pole of the Earth is a magnetic south because of the attraction. Magnetic poles, even though this is predicted theoretically, magnetic poles have never ever been separated. So if I take this magnet and I break it in two, I'm going to get two smaller magnets. If I take those and I break them in two, I will get two smaller magnets. And I can break them and break them and break them until I get down to the atom level or a quark level. Those things will have north and south poles. Okay, so there has never ever been a pole by itself. A north and a south always have to be together. So that's super cool. So that's where we're different here. Magnetic forces are kind of similar. Like poles repel, opposite attract. Magnetic forces are proportional to 1 over r squared, just like electric forces. So that's a summary. Again, there's lots more in your textbook. That's kind of the highlights of it.
So if the poles were to switch, will we be in technically the southern hemisphere?
Yeah, that's a good question. Somehow I doubt it. Nobody's going to change all the maps, right?
It's going to be a lot more fun figuring out which pole you're on.
Yeah, it'd be fun, right? They have to relabel the compasses or something. Magnetic field lines are something we can draw. Here's pictures I took out of your book, so I didn't want to draw them yourself. You can map them out. I got this little doodad. We've had this for a long time. And it's essentially just a bunch of little compasses. Hopefully you can see the little arrows. If I put a magnet on it, it will start to map out the magnetic field lines. See how they're shaped. So that's a magnet by itself. Goes into the south out of the north. If I put a north and a south together, it'll go out of the north right into the south and then twisting around. I can put a north and a north together, and they're kind of swishing out from each other. So there's the picture from the textbook. The field lines are similar to our field lines that we did with electric fields. They'll never ever cross. That would mean that the field had two directions at the same time. That doesn't happen. A vector can only have one direction. The field is weak where the lines are far apart out here. The field is strong where they're close together and close to the magnetic poles. So kind of same deal that our electric field stuff had. Okay, now this last bit, I think this is so cool. Some might argue that it belongs more in Physics 1021, which is more biological than this course, but I think we should have it here too, is magnetic navigation. Okay, so this is observable in animals. So birds, I got some bats, and whales, I don't have a picture of a whale, they navigate, they migrate partially based on magnetic fields. And this is kind of why I think the whole flipping of the poles is really interesting. Because clearly when the poles flip, the whales are not going to get lost and travel north instead of south, right? So kind of how entirely does that navigation work? But anyway, a lot of animals have a magnetic sensor in their bodies, just like the way we feel gravitational fields, right? We know to fall down when we trip up. Animals feel magnetic fields, so they can feel those lines. I think that's really cool. Some creatures, like tortoises and fish and little rodents, you can see that they'll follow the Earth's magnetic field lines. So like turtles will walk along the field lines to get to the water. So when they come out of their eggs, when they're born in the sand, and crawl towards the water, you can trace out the field lines of the Earth. So that's really cool. I only have one dog, so I can't do an experiment on it. This is not my dog. It's from an internet friend. But apparently dogs, if they're off leash and you take them outside to kind of do their business, they will line up along the Earth's poles. Likewise with cows, a field of cows, when they're just free grazing, they will line up along the magnetic field lines of the Earth. So they have these sensors too, right? Like, I think that's so cool. This is a picture of a little bacteria who lives in the ocean. So this little bacteria in the ocean, I check the time, make sure I'm not going over. This little bacteria in the ocean, he needs to live down close to the bottom of the ocean to get the right oxygen levels to breathe. If he goes up too high or down too far, he won't be able to breathe and he'll die. So down at the bottom of the ocean, it's dark, right? And he doesn't have eyes anyway. He can't see where up is and where down is. So how does he know where up and down is? There's a little bit of iron in him. So that little bit of iron will line up with the field lines, and he follows that till he gets to the right part of the ocean where he can survive. So that lets him know how to stay at the right depth. So this is kind of applications of magnetic fields. So it's really cool. It's really worth studying. Yeah, and it's kind of good to know about. So the next thing we're going to do is talk about forces on moving charges. But why don't we wait and start that on Wednesday? So we'll quit here with the conceptual stuff, and we'll do that on Wednesday.